Chapter 10 involves comparing two populations or groups, and the first section involves comparing two proportions. So let's look at some details here. In this section, we will describe the center shape and spread of the sampling distribution for the difference in two sample proportions, determine whether conditions are met in order to do inference about P1 minus P2, construct and interpret confidence intervals to compare two proportions, and perform significance tests to compare two proportions. So suppose, for example, we want to compare the proportions of individuals with a certain characteristic in population 1 and population 2. We'll call those characteristics the parameters of interest, P1 and P2. Now, ideally, I'd like to take a simple random sample from each population and compare the sample proportions of that characteristic. So what if we want to compare the effectiveness of treatment 1 and treatment 2 in a completely randomized experiment? This time, the parameters P1 and P2 that we want to compare are the true proportion of successful outcomes for each treatment. We use the proportion of successes in the two treatment groups to make the comparison. So we have two different populations. The parameters are P1 and P2. The statistics are P hat 1 and P hat 2. And then the sample size, of course, would be N1 and N2. To explore the sampling distribution of the difference between two proportions. Now this sounds confusing, so let me say that again. To explore the sampling distribution for the difference in two proportions. In other words, the subtraction of P1 and P2, the difference in how different those two proportions are. Let's start by looking at these two populations. So we have one school where 70% of the students did their homework last night, and we have another school where 50% of the students did their homework last night. So the counselors at each school take random samples of students and record the proportions that did their homework. Now notice they took different sample sizes. At school 1, they took an SRS of 100 students, and at school 2, they took an SRS of 200 students. So school 1, they asked 100 students, hey, did you guys do your homework last night? Now we know the whole school did 70% of them did their homework. So perhaps 70-ish of these students did. And likewise, half-ish or around 100 of this counselor's sample will have done it, but not necessarily exactly. So what can we say about the difference in counselor 1's sample proportion and counselor 2's sample proportion? Well, we used some software, Fathom, it's a statistical software package, and generated 100 simple random samples of 100 students from school 1, and that's what's in this graph right here. This shape is approximately normal. The center of this graph, if we've done it enough times, will be 70% because that's what school 1 was. And the spread is going to be 0.7 times 0.3 over 100 rooted, or that number. Now this is for school number 2, and this had 200 students, and the center of this was 50. That's a little bit less smooth than my other one, but that's okay. It's still approximately normal with the center at 0.5, and the spread is going to be the square root of 0.5 times 1 minus 0.5 over 200. Now this distribution here is the sampling distribution of the difference in these two proportions. In other words, we call counselor 1 and counselor 2, and they each take samples and they each get their p hats, and we subtract those two numbers and make a dot. And then we do it again, and 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 again. And that eventually turns into a graph that looks similar to this one, the difference in the two proportions. Now, for reasons we'll go through in just a minute, the center of this graph is the difference in my two p hat, or my two p's. So 0.7 and 0.5, that's why this is 0.2. And the standard deviation of this graph is 0.058, and I'll explain that some more in just a second. So this graph is giving me an idea about how different my samples are. P hat 1 and P hat 2 are random variables, and the statistic P hat 1 minus P hat 2 is the difference in those two random variables. Now back in chapter 6, we learned that if these two variables are independent, we can find their mean, the difference of their mean, by subtracting the two means. And we can find the variance of the difference by taking sigma squared x plus sigma squared y. And you recall that change to a plus, similar to Pythagorean theorem. And we looked at variance here instead. Don't get too bogged down in this, but this is the theory behind it if you need to stop and ponder how that works for just a second. So consider this. Choose an SRS of size N1 from population 1 with a true proportion of success of P1. And independently, a different SRS of size N2 from population 2 with a proportion of success P2. Provided these conditions are met, the shape will be approximately normal. So what are the conditions? Well, similar to what we have before, we need each group to have at least 10 successes and 10 failures. In other words, N1P1 needs to be bigger than 10, N11 minus P1 bigger than 10, N2P2 bigger than 10, and N21 minus P2 bigger than 10. 10 successes and 10 failures in each group, and then we'll have an approximately normal distribution when I combine those two things to find the difference. The center of the sampling distribution will be the difference of P1 and P2. The center of the distribution will be the difference of P1 and P2 because that's what we get from having a random sample, no bias. The standard deviation will be found using this formula that we talked about from chapter 6 and applying it to this stuff. So it looks like this: the square root of P1, 1 minus P1 over N1, plus P2 times 1 minus P2 over N2, provided that the 10% rule is met. So that formula is the standard deviation of the sampling distribution. In other words, the shape is approximately normal, provided that I have 10 successes and 10 failures in each group. The center of the graph is the mean, and the standard deviation is found by this. Now, when I look at all those different, the P1 and P2s, and I subtract them to get the sampling distribution, as they populate a graph, it will take this shape with this middle and this spread. So, suppose there are two large high schools, each with a lot of students in a certain town. At school 1, 70% did their homework. At school 2, 50% of their students did the homework. We took an SRS of 100 and an SRS of 200. What do we have? Let's look at it and show you what I came up with in that previous table. Okay, so at the first school, 70% of 100 is what's expected to do their homework. That's 70 students. 30 of them I expect not to. Both of those are bigger than 10. In school 2, how many students do we expect to do their homework? Half of them. So that's 100. And how many would not do their homework? Half of them. So that's 100. Both of those are more than 10. So since all of those numbers are bigger than 10, the distribution is approximately normal. The middle will be the average for, or the true proportion for population 1 minus the proportion for population 2, which is 0.2. And the standard deviation, we'll use this formula. This information came from the first school, and this information came from the second school. When the data comes from two random samples or two groups in a randomized experiment, the statistic p hat 1 minus p hat 2 is our best guess for the value of p1 minus p2. We can use the old familiar formula to create a confidence interval. Statistic plus or minus a critical value times the standard deviation of the statistic. So when the 10% condition is met, we can use that formula for standard deviation. And if the normal condition is met, then we can use a z-star to get that critical value. Here that is written down another way. That's the same information. Now we don't actually know P1 and P2, because if we knew P1 and P2, we would just know what the difference was and would be done with it. So in a confidence interval, we're going to use the next best thing, P hat 1 and P hat 2. This result It's called the standard error of the statistic. That is what's going to come after the critical value in the standard error or in the confidence interval formula. That tells me that's where my z star is coming from because I have a normal distribution. And so I could plug the numbers in, p hat 1, p hat 2. So I only actually took the samples once. This is counselor 1's estimate. This is counselor 2 estimate. Subtract them. Maybe this is, 1.96 if I'm doing a 95% interval. And then counselor 1's estimate over 100, counselor 2's estimate over 200 because counselor 2 took a bigger sample. Now what if I wanted to do a significance test? The observed difference between two sample proportions can reflect an actual difference, or it might just be due to chance variation. Significance tests help us figure out which explanation makes more sense. Just because counselor 1 and counselor 2 got different answers, it doesn't mean the truth is different. It might have just been luck. So the null hypothesis generally says P1 minus P2 equals, in this class, 0. That means there's no difference in the two. If P1 minus P2 equals 0, then they equal each other. And the alternative hypothesis could either be greater than 0, less than 0, or perhaps the two-sided not equal to 0. Conditions look very similar to what we have before. And my test statistic is just like we've done in the past. The test statistic is the statistic minus the parameter over the standard deviation of the statistic. In other words, p hat 1 minus p hat 2, that's my statistic. The parameter is really p1 minus p2, which we are hypothesizing to be 0. So that's why this is a 0. And then this standard deviation of the statistic is that square root stuff we talked about before. Now, it turns out if P1 equals P2, if that's in fact true, then the two parameters are the same. And we could just call them P because there's no difference between P1 and P2. If we want to estimate P, it makes sense to combine both samples to get a bigger sample size. This is called a pooled or combined sample proportion. It's how many successes we got total divided by how many people we asked total. In other words, if there's no difference in these two schools' homework completion rate, then I take the total number of students that said yes, whether it was to counselor 1 or counselor 2, that goes on the top, and the total number of students asked by either counselor, and that goes on the bottom. That's the pooled p hat or the combined p hat as they use this C here. On the bottom of my test statistic formula, in the denominator, this square root stuff, I'm using the pooled p hats right in here, or the combined p hats. That's the formula for my test statistic. We'll calculate the p-value by deciding how far away this z is in one of these graphs, whether it's a one-sided graph or a two-sided graph, just like we've done before. Inference for experiments. Many important statistical results come from randomized comparative experiments. Defining the parameters in experimental settings is a bit more challenging. Most experiments on people use recruited volunteers as subjects, and when those subjects are not randomly selected, researchers cannot generalize the results of an experiment to some larger population of interest. Researchers can draw cause and effect conclusions that apply to people like those who took part in the experiment. If the experimental units were not randomly selected, we don't need to check the 10% condition because that has to do with selecting things from a finite population. In this section, we talked about describing center shape and spread of a sampling distribution for the difference of two sample proportions. We determined whether the conditions were met. We talked about constructing and interpreting a confidence interval to compare two proportions, and we performed a significance test to compare two proportions.